welcome back to Gamma Die Gamma. So I'd like to point out that today is the 14th of Feb. Today is Valentine's Day. I'm single. Most of you might be single and I don't know. But the thing is, I love physics. So today we are going to be doing a little physics. I got many requests saying, Rudra, do some magnetic effects of electric current video, and that's because the ISC board exams are near. So today I'm going to be legitimately doing a magnetic effects of electric current essentials video, mainly from the perspective of an ISC board exam. But if you're not in that board, if you're not doing an ISC curriculum, please don't feel discouraged to keep on watching. So let's get to it, guys. So like electrostatics, there is like a general formula for a magnetic field this time instead of force directly, which mu naught by 4 pi times IDL sine theta per r squared. And now this is what we call the Sowards law. And this is a law which was, this has no derivation because this was made clearly with observation, just like your Coulomb's law of electrostatics, built on observation. So the way this works is, if you have a current carrier, conductor, obviously, you have a differential length element, call it dl bar, and you have to find the magnetic field at point P. So then you draw a radius vector, position vector to that point, call it r bar, and the angle between the dl bar and the r bar, call it theta, and the current through this conductor is I. So the magnetic field at point P is given by this above statement of the Sowards law. Okay, and now we want to actually use this Sowards law to an extent. So the first case is when we have a circular loop which carries current. Again, we can call the current I. Then we have, say, a differential length element on the circumference, call it dl, and it's tangential to the surface. And then they tell you to find the magnetic field at the center. So from that dl element we can draw a position vector, call it r bar. And if you know the properties of circles, the radius and the tangent are perpendicular to each other at a given point. So basically now we can plug everything in the Sowards law formula. So dB is equal to mu naught by 4 pi times I dl as it is, sine of 90, because see, theta was the angle between the infinitesimal length element and the position vector. Here the angle is 90 degrees. So sine of 90 degrees over r square. R, that's just r. So we have an equation for dB, and if we want to find the total magnetic flux, we have to integrate this. So when you integrate dB, you just get B. Mu naught by 4 pi is a constant. Over here, if you notice, the radius vector is a constant. The radius of a circle is a constant value. So you can just pull that out too. Now the current we assume is constant. Sine 90 is 1. So it's essentially integration of dl over the length, and the length is from 0 to 2 pi r. Basically, length is the circumference of the circle. You start from 0, you go full round, you have 2 pi r. So yeah, we can clean this up further. So B is equal to mu naught by 4 pi I by R squared times, when you integrate dl you have L, and then you plug in the upper limit 2 pi R minus 0, which is 2 pi R. So this R, that R cancels out. Okay, so finally we have an expression for B. So mu naught by 4 pi times 2 pi times I by R. Now this was when you have just one turn of it. If you have, say, n turns of this coiling around, and you wanted to find the magnetic field at the center, you would just multiply by the number of turns, because when n was 1, this was only true for one turn. You can just multiply. Simple analogy. Now this result was for a circular loop of wire, but instead of a loop, say someone tells you to find the magnetic field at the center of something like the sector of a circle, and you have an angle alpha. Okay, so basically instead of this 2 pi, you just put the alpha in. So mu naught by 4 pi alpha I by R, and then you can multiply by the number of turns if there are any. And you might say, why does this trick work? Why, just because your circle has 2 pi radians, right? The entire angular measure is 2 pi radians, and here the angular measure was alpha. You just replace the 2 pi with an alpha. Why does this work? Well, let me remind you, we were integrating over the entire path. In the case of the circle, the path was from 0 to 2 pi R. In this case, it's just this distance, this arc length. So radius times angle. That's how that works. Arc length is radius times angle in radians. That's how that works. And this basically is, they'll rarely ask you, but if they do for small MCQ type questions, then you know what to do. Just replace the angle, whichever angle you have. This is only for the center, okay? Magnetic field at the center. Point is important for the magnetic field, or even if you say have an electric field. In this case, a magnetic field. Now you can also find the magnetic field due to a current carrying wire at a point, say P, a wire with, say, definite length. And in this case, I'll just directly state the formula. So the formula goes like this, and the proof is long and rigorous. I mean, people have used the Sowards Law and done some substitution. So directly the formula is mu naught by 4 pi I by R sine of phi 1 plus the sine of phi 2. And phi 1 and phi 2 are basically the angles that the top part subtends with the central part that's that's connected to the point where you want to find the magnetic field. And now this is interesting, because as this wire gets infinitely long, then this phi 1 goes to 90, phi 2 also goes to 90, and so they have sine 90 plus sine 90, which is a 2. So for the infinitely long case, the formula is mu naught by 4 pi 2I by R. And now this is the most important formula, I'll say, in this unit. We're going to be using it a lot to, solve questions and stuff. But this they rarely ask. I'll probably do like one sum if you want. But before jumping into any questions, I forgot to tell you this: how to find the direction of a magnetic field due to a current carrying conductor. So this is what I call the right hand thumb rule. Very useful rule, and it's always with the right hand, as the name suggests. So what you do is, if you have a current carrying conductor, okay, then you take your right hand and curl it, and place the thumb in the direction of the current carrying vector the current carrying wire. So the current going on top, so my thumb is on top, and then my fingers are curled in the direction of the magnetic field. So basically, my thumb is, you can do this if you can pause the video and do this if you want. So your thumb should be pointing upwards, and then curl your fingers around your thumb. So that's the direction of the magnetic field. So the magnetic field is going around like that. Or you can say that the magnetic field is going into this paper, into the plane of the paper, and then from here it's originating from the paper. So basically, behind the paper is just curling around, and then from the top it's again originating from here and then going back here. It's like a loop. Magnetic fields are like loops. And this convention is weird. You might find it weird, but I'll remind you how to. I'll give you a technique that will help you remember. So, if you've read comic books, if like a comic book character is pierced or stabbed, the wound is like this. So that's the same thing as a magnetic field piercing the paper. Just look at this. The magnetic field was going into the paper here. So the paper is being pierced, and the other sign, you can say the arrow top, is when the magnetic field emerges. So this emerges, and this say penetrates. That's your convention of the magnetic field. So always use the right hand. Always place the thumb in the direction of the current in the conductor. Over here the current's on top. So my thumb's on top. But if say my current were going like this, then I would place my thumb below, and then the direction of the magnetic field would completely reverse. You can try that out with your right hand. So yeah, this is what's important. This is the sign convention for the direction of the magnetic field. So yeah, let's get into some sums now. Now, using the last formula we had, let's do a question. We have a square. Please forgive my bad drawing skills. We have a current carrying square. Sounds cool, yeah, I know. So you have a current going like this, and say the side of the square has a length A, and so the distance from the center of one side to the central point of a square, the angle is obtained is 45 degrees, and you can use some geometry the distance from the center of this side to the center of the square, the distance is a by 2. You can use some trigonometry and geometry and just find out why it's a by 2. For now, I'll just state it's a by 2. And now they're telling us to find the magnetic field at the point at the center O. So basically now you should understand that the total magnetic field contribution at O, B net, let's say B net, is because of side AB, side BC, side CD and side DA. So 4 sides contributing to the BAB. Since it's a vector, we'll have to do a vector addition. BC, CD and DA. Okay, let's just do BA first. We can first just solve for the magnitude. We can use mu naught by 4 pi. We know the angle. I by R, using the previous formula, sine phi 1 plus sine phi 2. Because it's not like it's an infinitely long conductor. It has definite length, and even we know the angle. We know phi 1 and phi 2. So we can just plug in mu naught by 4 pi times I over then the distance from the current carrying wire to the point where we want to find the magnetic field, a by 2 in this case. I just told you this distance is a by 2. Remains the same on top. Then sine 45 degrees is 1 over root 2. Sine 45 degrees again is 1 over root 2. Now when you simplify, you get mu naught by 4 pi 2 root 2 I by A, and that's just for BA. And the direction of BA, you want to use the right hand thumb rule, you can. It's pointing, it's originating. So magnetic field are originating from O. So now the magnitude, it so turns out, of the magnetic field due to BC is the same as BA, the magnitude I'm talking about. The magnitude is same, but let's check for the direction. So BC is equal to BCD is equal to BDA is equal to BAB. Just so happens, because you can use the formula on any one side and then you'll know this holds true. Let's check for the direction. You can use the right hand thumb rule, and again the magnetic field emerges. Over here the same thing, the magnetic field emerges from O. Magnetic field emerges from O. Magnetic field due to this current carrying wire. So all the current carrying elements which can generate a magnetic field, which contribute to a magnetic field at O, all of the magnetic field vectors are pointing outwards. So they have the same direction, right? Everything is coming out. So if two vectors have same direction and have equal, same direction, not equal, that is something else. But say if you have two vectors with the same direction, you can directly add them. So since this thing holds true, we can just multiply one magnetic field due to one element by 4. So in the end, we have B net is equal to 4 BAB. So which will be mu naught by 4 pi 8 root 2 I by A, and since everything was pointing outwards, the resultant will also point outwards. It will emerge from O. And I can't show a 3D diagram here, but I think you get the idea. It will just come out of this sheet. Now we have something called as with something called as Ampere's Circuital law, and this is actually the equivalent of Gauss's law in electrostatics, if you remember. I hope you do. Both these chapters, magnetism and electrostatics, are analogous to each other. So anyways, now what this thing says that the line integral of the magnetic field over a closed loop is mu naught times the net current threading through the loop. So, if you have something, say like a wire that's going through, the wire obviously carries current. Everything has current here. Wire carries some current. So the magnetic field due to this wire, the line integral of the magnetic field due to this wire is mu naught times the net current which is going through this closed loop. So you'll have to integrate the magnetic field over this closed loop. Okay, so let's go ahead and do one derivation. We can also derive the infinitely long conductor, which was a special case of the Sowards Law formula that we talked about last time. You can also derive that using Ampere's Circuital law. Let's go ahead and do that. Have an infinitely long conductor. You construct an Amperian loop, and we have to fix this. We have to design this according to our requirements, just like we did for the Gaussian surface. And the loop is always taken in the direction of the magnetic field. So magnetic field due to a straight line conductor was in circular loops around it. So that's how we are going to take our Amperian loop, so that the magnetic field passes exactly through it. Now let me define a differential length element dl, because we need to integrate using that. Again, tangential direction, and so basically now we have to integrate over this loop. We have to perform a closed integration. So b bar dot dl bar is equal to mu naught I. You can instead of writing a closed integral, you can write a regular integral, but set the limits as 0 to 2 pi r, because that's the entire closed loop. We're integrating in the direction of the magnetic field. That takes care of any negative signs that may pop up. Okay, so even the magnetic field is in the direction of the infinitesimal length element dl. The dot product is basically b dl cos of the angle between them. The angle between them is 0 degrees, is equal to mu naught I. Cos 0 is 1. B, will assume that it remains constant at a fixed distance r from the current carrying wire, and it's uniform over this loop. And physicists make a lot of assumptions. So integrating dl from 2 pi r to 0 is just 2 pi r, and mu naught I. So we can rearrange this mu naught by 4 pi into 2I by r. And you could have said, I can just cancel this 2 out and have mu naught by 2 pi, just like you would obtain by rearranging it directly. But I say this is a constant value. The mu naught by 4 pi is a constant that we know, and they provide you in the question paper also. it's 10 to the minus 7, this constant. And because for finding mu naught again, we'll have to multiply by this factor of 4 pi, and then it's just better to write this as mu naught by 4 pi. And see, we have the same formula again. Now that's one application of Ampere's circuital law. There's another for a solenoid, but first I would like to do some questions relating to infinitely long conductors, charge carrying wires. So the question says that we have two infinitely long current carrying wires whose directions of currents are in opposite directions. This has 20 amperes of electric current. This has 30 amperes. And they're telling us to find magnetic fields at three different points, P, Q and R. And obviously they've given us the distances. So from wire 1 to P, the distance is about 10 centimeters. And then from wire 1 to Q, again 10 centimeters. But the net distance between wire 1 and wire 2 is 20 centimeters. The distance from wire 1 to R, wire 2 to R is 10 centimeters. And they're telling us to find magnetic fields at P, Q and R respectively. So first let's do it for P at P. Now first let's identify the directions of the magnetic field. That will help us understand if we want to add them directly or subtract them, because they're vectors, right? We need the direction first before doing anything. So at P, if you use the right hand thumb rule on wire 1, the magnetic field is going to emerge. The magnetic field of wire 1 is going to emerge at P, but the magnetic field of wire 2 is going to penetrate P at P. So one's emerging, one's penetrating. We have to subtract because the angle between them is 180. They are in opposite direction exactly. So yeah, we can find first the magnitude of magnetic field of wire 1, B1, is mu naught by 4 pi into 2I1 by R1, let's say. So mu naught by 4 pi, current is for 20 and 2 into 20, 40, all over. And now this distance from wire to point P is 10 centimeters, which we can write in meters as 0.1. Unit of magnetic field is Tesla, and as I said, it's emerging, so you can just put this sign beside it. And just evaluate this if you want. This is 10 to the power of negative 7. This will just become 400. So this is 4 into 10 to the power of negative 5 Tesla, and it emerges at P. Now you can just find V2. V2 is going to be mu naught by 4 pi to I2 by R2. This is mu naught by 4 pi. 2 into 30 is 60. And now the distance is 30 centimeter, which is 0.3 meters. You can simplify this 10 to the power of negative 7 into 200, sorry. And 2 into 10 to the power of negative 7 Tesla, but it's penetrating it. but as we said, the directions are opposite. So the magnetic field at point P, BP, is equal to B1 minus B2. Since wire 1 is closer to P, the strength of each magnetic field will be greater than the strength of the magnetic field of wire 2 at P, because wire 1 is closer to P. So B1 is greater in magnitude, B1 minus B2. So resultant you can expect to be in the direction of B1, which you can expect it to be emerging, the resultant. So you subtract it, you get 2 into 10 to the power of negative 5 Tesla, and it's emerging. Now let's do it for point Q. Now at point Q, let's check for the direction. Okay, so the magnetic field due to wire 1 will penetrate at Q, and well, even the magnetic field due to wire 2 will penetrate. Wire 1 and wire 2 both will penetrate. So basically you know that BQ is B1 plus B2, and you can guess, since both are penetrating, the resultant would also penetrate. But let's find the direction in the end. So let's find B1. So mu naught by 4 pi. I won't write the formula this time. I'll just directly substitute 2 into 2040 over, now the new distance is 10 centimeters because it's point Q now. So 10 to the power of negative 7 into 400, like before, is 4 into 10 to the power of negative 5 Tesla, but it's penetrating. Do the same for B2 now. Mu naught by 4 pi times 60 over, again the distance is 0.1 meters. So 10 to the power of negative 7 into 600 is equal to 6 into 10 to the power of negative 7 Tesla, and it will penetrate. So BQ is finally the addition of these guys. 10 into to the power of negative 5 Tesla, and it's penetrating. Since I write the magnitude and direction both, I'll need to add an arrow on top. You can, again, if you want, you can simplify this to 10 to the power of negative 4 Tesla. It will penetrate. And I think this is equal to 1 Gauss in the CGS unit system. So yeah, we have the magnetic field at point Q due to resultant magnetic field at point Q. Now let's do it for point R. So at R, let's check for the directions. Now magnetic field due to wire 1 will penetrate point R, and then the magnetic field due to wire 2 will emerge from R. Now again we have to subtract. So BR is equal to B2 minus B1, because see, now wire 2 is closer to point R, so its magnetic field will be stronger. So so B2 is greater than B1, so B2 minus B1. Let's find the magnitude of B1. So mu naught by 4 pi, 2 times 20 is a 40 over, now the distance is 20 and 10, so 0.3 meters. Now this is 10 to the negative 7 into 400 by 3, so 4 into 10 to the power of negative 5 by 3 Tesla, and it will penetrate. We can do for B2 also. Mu naught by 4 pi, it's 2 times 30, 60 over 0.1 meter. 610 to the power of negative 7, 6 into 10 to the power of negative 5 Tesla, and it will emerge. So B2 minus B1, so BR bar is equal to basically 6 minus 4 by 3 into 10 to the power of negative 5 Tesla, and it will emerge. And let me just approximate the value. 6, so it's around 4.66, and 6 is recurring, so you can just write 67 into 10 to the power of negative 5 Tesla, and it will emerge from point R. So the last application you can say of Ampere's circuital law is the magnetic field due to a solenoid. Okay, so first, if you done some 10th grade physics, a solenoid is like a coiled piece of wire, and the magnetic field is basically something like this, a solenoid through the loops. Actually, I drew the loops a little small, so I'll be just drawing the magnetic field because this will make the entire derivation shabby. So the magnetic field looks cool. It's something like this, almost like a bar magnet. Just one more line, and we can draw or select the Amperian loop on the top portion of this. So this is B, A, C and D, and remember what Ampere's circuital law said. The closed loop integral of B bar dot dl bar is equal to mu naught times the net current through this thing. So anyways, so we'll have to basically do an integration over length BA, AD, DC and CB. So we can break this closed loop integral into integral from B to A of B bar dot dl bar plus integral, we have to maintain the order, so B to A to D of B bar dot dl bar plus the integral from D to C B bar dot dl bar. Finally the integral from C to B of B bar dot dl bar. And now many terms are going to cancel out, because look over here, the magnetic field and the dl element on this side AD, they are 90 degrees with each other, so the dot product or cos of 90 is 0, right? This thing will just go away, and so will CB, even that length element dl is perpendicular to B bar. So and in the end even CD will go away, because there is no magnetic field outside this region of influence. There is no magnetic field through CD. So like the magnitude is 0, so this term will just go away. So finally we are left with the integral from B to A of BDL, because now no need to write the dot product, we can cos 0, because angle between the magnetic field and the length element is 0, so cos VO1. Let's call length AB x. Let's call this length x. So finally you just have Bx when you integrate. Now Bx by Ampere's Circuital law is mu naught I, but you also need to have a term for the number of turns, because the solenoid strength is all in the number of turns. I mean that's how much current you will have. It's like a multiplicative factor for the basically total current through a solenoid. So we can just rearrange mu naught I n by x. X was this distance and n was the total number of turns. So we have total number of turns per this length x. We can call that quantity the number density. Basically the number of turns per unit length. Here our length is x, so we assume this to be uniform so that this holds true. The number density is uniform. So mu naught ni or mu naught in. And remember, even when you are solving numericals, this formula is also very important when you're looking at numericals. That this term, this small n, is basically the number of turns, total number of turns per unit length, the number density. Don't forget that. Don't confuse the small n for the capital N. Many people do. If you want a better intuition for why we multiplied by the n, remember that it was the in the definition of Ampere's Circuital, it was the net current threading through the Amperean loop. This was our Amperean loop, and this is just the inside part of the solenoid. So our solenoid is curled up like this. So for one turn, say current I passes. For 2 turns, 2I passes. So for n turns, Ni will pass. Net current threading through the surface. So that's why we multiplied by n. Now we've talked a lot about the magnetic field. Now let's talk about the magnetic force. So you might recall that in electrostatics, when you had a charge Q in an electric field E bar, it experienced a force equal to E bar times Q, right? But now charges in magnetic fields also experience force. Yes, they do, but only when they are moving. So suppose this charge is moving like this, and at this point, say the magnetic field penetrates the surface, then the force experienced by this charge would be inwards. It will be inwards over here, and when it has a straight velocity, when it goes ahead, it will again be inwards. And let me remind you what kind of motion happens when you have velocity and force, or let's say acceleration, are when they are 90 degrees with each other. That's right, uniform circular motion. Now the formula for the force given by Lorentz was F bar is equal to Q bar times V bar cross B bar, or you can just write the magnitude as QVB times the sine of angle between B and B bar. Only moving charges experience the magnetic force. If this charge was stationary and you place it in a magnetic field, nothing would happen. But electric field doesn't require such a condition. So charge needs to be moving, otherwise the velocity is 0 and the force is 0, the magnetic force. Now how to determine the direction of this magnetic force? Well, some of you guys who've paid attention in 11th grade, you guys might know that how to find out how to find the direction of a cross product. So I'll just remind you once again. So you have a velocity over here, and you have, say, magnetic field here. So when it's one vector crossed with another vector, so you place your right hand over here on the first vector, and the direction, the order matters, and then you turn it, then you turn your right hand towards the second vector, and then you raise your thumb, and the direction that your thumb is pointing, in this case it's like, sorry, it's coming out of, it's emerging out of this point. Direction which your thumb's pointing is the direction of the force. So now look at this example. The V bar is straight up, the magnetic field is inwards. Now if you can try this at home, you can place your right hand on the velocity and then curl your fingers downwards towards the magnetic field. Raise your thumb, and then thumb is pointing over here in the direction of this force. But let me remind you that this direction, as it were, this direction that you obtain by doing the cross product properly, is only for the positive charge. It is only for the positive charge, because a negative charge would experience the direction in the opposite, would experience a force in the opposite direction. So if I had, like, say, a negative Q over here, see, in the same magnetic field, it would experience the force over here. Or I can just put it this way, that if you have a negative charge in a moving negative charge in a magnetic field, you can do the cross product, you get the direction of a force, but then flip it up because it's a negative charge. But if it's a positive charge, don't flip up the direction of this cross product. And you might also rearrange this formula. So QVB you can rearrange, and you will get ILB. And when you have this, you can determine the direction of the force by just using the Fleming's left hand rule. So if you have, say, your thumb, pretty fat thumb, I know, your index finger and your central finger. So your thumb will point in the direction of the force, your index finger in the direction of the magnetic field, the central finger in the direction of current. You can say FBI. Now someone call the cops. So this is FBI, and remember, all the three are mutually perpendicular. So this is perpendicular to this, this is perpendicular to this, and this is naturally perpendicular to this. But if you were to apply your Fleming's left hand rule instead of the cross product to determine the direction of the force experienced by a moving charge, then you need to consider the direction of current. So current flows in direction of positive charge. So if positive charge is moving forward, current will also move forward, and you can use the Fleming's left hand rule, and you will get that even the force is again in the same direction. But now if you have a negative charge, then if the negative charge is moving forward, the current will move in the opposite direction, and then you can use the Fleming's left hand rule to know that the force will be indeed in this direction, that will be obtained by using the cross product in the flipping rule. So it's actually up to you which one to use. I would recommend using the cross product, which makes more sense to me rather, because later on it gets confusing whether to use the right hand rule or left hand rule, because right hand rule is for electromagnetic induction, left hand rule is for magnetic force, and it gets confusing after a point of time. So since we know that a moving charge in a magnetic field will perform uniform circular motion, so the magnetic force will be the centripetal force required to perform the UCM. You always need a centripetal force for uniform circular motion. So the magnetic force will be the centripetal force. This is the formula for the centripetal force. mv square by r is equal to, say, qvb. We just write the magnitude and say sine theta is just 90 degrees. So theta is 90, sine theta is just 1. You can just cancel one v out, and finally you have radius is equal to mv over qb, and since then you can find the time period, which is basically 2 pi m over qb. Time period is basically distance upon the velocity. You can just find that in. So time period, when in a magnetic field, if a moving charge executes UCM, the time period of one cycle is given by this formula. Now in some questions they tell us to compare the radii of two moving charge particles. Sometimes they have a proton. They tell us to compare it with an electron. They say that they are accelerated under the same electric potential. So basically the kinetic energy would then be that potential times the charge is equal to half mv squared. Velocity will then be 2v times q by m. You can just plug velocity in the radius formula. Radius will then finally, after some term shifting, will be 2m times the accelerating potential over qb. So these are the important types of questions. They might ask in MCQs and stuff. So if they're accelerated under the same potential, their kinetic energy will increase because they're being accelerated, right? And work is equal to change in kinetic energy. So work is the potential times the charge. Then you isolate V, make V the subject, plug it into the radius equation, then change the terms accordingly to the formula. If you're finding the ratio, then many terms will cut out. If you have the ratio of the radii of a proton and electron only, I think the mass term will be left because Q and B and accelerating potential are the same. So many things will cancel out. Now the applications of having a moving charge particle in a magnetic field is seen in the case of a cyclotron, which is like a miniature particle accelerator. So what happens is you have an AC source connected to two plates, and you have a moving charge here, and say your magnetic field is perpendicular to this. Your magnetic field is, say, pointing inwards, and you have a positive charge just projected like this. Okay, so because of this magnetic field, this positive charge would totally follow this circular path, because magnetic force will provide a centripetal force, will follow this circular path. But now what happens is, since it's an AC source, at the interval when say this thing will have a negative charge at that instant, the positive charge will be present at this point, and since this has a negative charge and this is a positive charge, there will be electrostatic attraction between them. So this initial circular path will get slightly deviated because of this electrostatic attraction, and when the particle comes back over here, at that point of time, since it's an AC source, we can time the frequency accordingly, that this will have a negative charge at that point of time. So again, the positive charge will be deviated, So it will be some sort of an accelerated circular motion, not uniform circular. It will be like an accelerated circular motion. And the great thing here is that the kinetic energy of the charge will increase, because see, in the UCM no work was done, so the change in kinetic energy was 0 before under UCM. But now, because of this accelerated circular motion, there will be an increase in kinetic energy, because there is an electrostatic force of attraction, which is, you can say the charge is getting slingshotted at this point. So due to this, the velocity of the charge will increase, because there is an acceleration going on. The velocity of the charge will increase, and the charge will be accelerated. So, this is, you can say, a miniature particle accelerator. And now you can time the frequency of the AC accordingly, because we know the time period of each revolution now, don't we? You can just invert it. You have the frequency of your AC source, QB over 2 pi m. That should be the frequency of your AC source, so that when the charge completes one cycle, then the polarity changes at exactly that point, and then again. So this was your cyclotron. They might ask you as like a theory question, not like a numerical problem solving question. Now let's do a small problem based on electric force. So the question says you basically have current carrying wire, current of 5 amps running through it. You have an electron which is traveling parallel to it. The velocity of the electron is about 10 to the 6th meters per second. The distance of separation between them is 0.1 meter or 10 centimeters. And they're telling us to find the force, like the magnetic force on the electron due to this current carrying wire, and the direction of the force. We know the charge of the electron is 1.6 into the 10 to the power of negative 19 coulombs. Velocity is 10 to the power of 6 meter per second. And we don't know the force. Now, the force on a moving charge, the best formula that we know is QVB sine theta, right? We don't know the magnetic field. We know charge, we know velocity, we don't know the magnetic field. And we have an infinitely long conductor here, we can easily find the magnetic field. So the magnetic field of an infinitely long conductor is mu naught by 4 pi into 2I by R. R is given, everything is given, 10 to the power of negative 7 into 2 times 5 is again 10 over 0.1, 300, 10 to the power of negative 5 Tesla. And now using the right hand thumb rule, the magnetic field due to this current carrying wire will penetrate the point where the electron is. So it penetrates, and we can all plug everything in the force equation. We know the magnitude, so we know the Q 1.6 into 10 to the power of negative 19 into V is 10 to the power of 6, and then magnetic field is 10 to the power of negative 5, and then the sine theta. See, the magnetic field is pointing inwards, the velocity is in the direction of the current. They have an angle of 90 degrees, so sine of 90 degrees is 1. This will just be a 10. So finally you have 1.6 into 10 to the power of negative 18 newtons. Remember, this is force, and I can also write for the direction. So let's use the cross product. So the cross product is V bar dot B bar. So velocity is upwards, magnetic field is downwards. the force should point towards the wire, but since it's a negative charge, we'll flip the direction of the force. This is where the force would point, or you can say away from wire. Or if you want to do it by the ILB method, the Fleming's left hand rule, so the current is going down, magnetic field is going inwards, so the force would naturally go away from the wire, right? Current and negative charge go in the opposite direction. Current is in the direction of the positive charge by some stupid convention, but anyways we have to follow it. So 1.6 into 10 to the power of negative 18 newtons away from the wire. That's the information about the force. So now we have an article which says that what is the force between two current carrying wires. Say current I1 going through this, current I2 going through that. I'll call this B, call this D. This distance R, and then since this thing carries the current, the magnetic field between these two wires due to wire 1 is inwards, due to wire 2 it will be outwards. You can do the right hand thumb rule. Okay, so let's calculate. This wire, I'll call it AB. This wire is CD. So we'll calculate the force on AB as I1, L and B2. So ILB sine theta is 1. So this is the magnitude now. Now the magnetic field that was producing a force on wire 1 is not its own. I repeat, a wire itself does not, basically when a wire carries current, the current has a magnetic field. So that magnetic field never causes any force on that source, on the source wire itself, because it was always around it, right? It's never at the wire, the wire's own magnetic field. So the force on a wire is never due to its own magnetic field. It's always due to the other's magnetic field. So the magnetic field, which is affecting the first wire, is the magnetic field of wire 2. So B2. We know the formula for B2, infinitely long conductor. So mu naught by 4 pi into 2I2 over say R, and we can just rearrange this as FAB over L, force per unit length, is given by mu naught by 4 pi into 2 times I1 I2 by R. This is for the force per unit length of on the first wire. Force per unit length on the second wire, it so happens you can do all the steps again, is mu naught by 4 pi into 2 I1 I2 by R. Yeah, both of them have the same force per unit length. This almost reminds us of the formulas of electrostatics, where we had two charges and the force between them was the same, but their acceleration depended on their value of charge. Let's just take the example of gravitation. So you have a big mass capital M and a small mass m. So the force between them would be the same. So like the same force would act on this mass due to this mass, and the same force would act on this mass due to this mass. But then their acceleration would be dependent on their mass. So for the same force, the small mass would accelerate more, the capital mass would accelerate less. That's why when the Earth pulls on an astronaut in outer space, the astronaut accelerates fast, not the Earth. I mean, The Earth also experiences a force, but the Earth's mass is so much compared to an astronaut that it doesn't matter. So it's almost like the same thing here. The force is the same. That's what I want to say. So let's do one numerical question on this thing. So say you have a wire on top, Q, 25 amps of current, and a wire below it in the opposite direction, P, 50 amps of current. Now since this is on top, this has a weight. Distance between the wires is R. Now the weight of Q per unit length has been given in the question, 0.025 Newton per meter. And now from our previous derivation, we know that F by L is mu naught by 4 pi into 2I1 I2 by R. And the question says that at what distance should we maintain, what distance should we maintain between these two current carrying wires, so that the first wire does not fall down due to its weight. So that's to say that the repulsive force, magnetic repulsive force between them, or let's say the magnetic repulsive force per unit length, should be equal to the weight per unit length. Then only by Newton's second law there will be no external force acting on it, and then it will remain suspended, it will levitate. So yeah, instead of force per unit length, we want it to equal to the weight per unit length. So 0.025 is equal to 2 into 10 to the power of negative 7 into 25 into 50 all over R. Now I'm quickly going to solve this. It's 10 to the power of negative 2 meters. And this is essentially how your maglev trains work. Now one thing I forgot to mention in the last article is that if you have two parallel wires with the current in the same direction, then the force between them will be attractive. But if you have two parallel wires with directions of current opposite in each of them, then they would experience a repulsive force. This is somewhat reminiscent. This reminds us about our electrostatics. So unlike charge is attracted and like charge is repelled. So it's quite similar to that. So that's why in this example that we did, the direction of current in the two wires was in the opposite direction. That's why there was a repulsive force between them. So this Q would move away, then even P would move away. So this force, the force of moving away per unit length, would be equal to the weight per unit length. Then only the net force on this would be 0, and it would remain suspended in air by Newton's second law. So this is basically what they use for the maglev trains, the principle behind maglev trains. I hope you guys enjoyed the video. If you have any doubts, please feel free to comment. I know physics, they've given less days for us, and if I have time, I'll be doing some more essential videos like these for math, and probably one more video on alternating current if you want. You can always subscribe to my channel, like and share if you like the video, and have a great day.